Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. To comprehend the work of Leonhard Euler is to confront an intellectual output of geological scale. His collected writings, the magnificent opera Omnia, currently span more than 80 large quarto volumes. This is a collection so vast that if a mathematician were to study it at a rate of 40 pages per day, they would be occupied for the better part of a decade. This imposing physical reality, this shelf-breaking monument of paper and ink, represents something far more profound than mere diligence. It is the architectural plan and the detailed masonry of a new mathematical world. Within these volumes, entire fields of inquiry are born. Existing ones are given a coherent language and structure for the first time, and the disparate threads of 17th-century discovery are woven into the unified fabric of modern analysis. His legacy is the very grammar of the mathematics and physics we use today, a contribution so fundamental that it has become almost invisible, absorbed into the very foundations of scientific thought. The world Euler entered was one of immense intellectual ferment, charged with the energy of the calculus. The heroic age of Isaac Newton and Gottfried Wilhelm Leibniz had bequeathed to the 18th century a tool of unprecedented power, the method of fluxions and the differential and integral calculus. It allowed for the description of motion, the calculation of planetary orbits, the finding of tangents to complex curves, and the measurement of areas under them. Yet, this powerful inheritance was something of a wild frontier. The methods were potent, their results often breathtaking, but they lacked a common language, a systematic organization, and a rigorous conceptual foundation. The calculus existed as a collection of brilliant, powerful, and often ad hoc techniques, employed with virtuosic skill by a handful of geniuses, most notably the formidable Bernoulli family in Euler's hometown of Basel. The crucial challenge of the era was to tame this wilderness of infinities and infinitesimals, to transform a set of brilliant procedures into a coherent, logical, and universally applicable discipline. Awaiting was the mind that could provide the syntax for this new and powerful speech. It was into this environment that Leonhard Euler was born in Basel, Switzerland, in 1707. His father, Paul Euler, was a Calvinist pastor and a man of some mathematical learning himself, having studied under the great Jacob Bernoulli. Following a well-trodden path, the elder Euler intended for his son a life in the clergy and directed his early education toward theology and the classical languages. The young Leonhard dutifully enrolled at the University of Basel to pursue this course. Yet, his prodigious aptitude for mathematics, a fire likely kindled by his father's own instruction, could hardly be contained. It was here that he encountered Johann Bernoulli, the younger brother of Jacob, and by then the reigning monarch of European mathematics, a figure of immense intellectual power and famously combative temperament. Johann Bernoulli quickly perceived that the young theology student possessed a gift of historic proportions. He began to tutor Euler privately on Saturday afternoons, guiding him through the most advanced mathematical texts of the day. As Bernoulli himself would later write, with a characteristic blend of pride and astonishment, I soon found that he was endowed with such a happy talent that he was able to grapple with any mathematical subject. I had to give him a problem to solve on his own, and when he came to me again, he would bring a solution which was often much more elegant than my own. This was a remarkable admission from a man who seldom praised anyone. The master recognized in the pupil a mind that could see with a clarity and breadth that perhaps even surpassed his own. Under Bernoulli's guidance, Euler rapidly absorbed the entirety of the known mathematical landscape, from the geometry of the ancients to the brand-new analysis of infinites. His destiny, It was becoming clear to all, lay with numbers and functions, with the abstract and eternal forms of mathematical truth. The opportunity for that destiny to unfold appeared on the eastern horizon, in the ambitious new capital of the Russian Empire. Peter the Great, in his quest to modernize Russia, had envisioned an imperial academy of sciences in St. Petersburg. It was to be an institution built from scratch, staffed by the finest minds that could be lured from the established intellectual centers of Western Europe. After Peter's death, his wife and successor, Catherine I, brought the project to fruition. The call went out across the continent, and Johann Bernoulli, acting as a chief recruiter, saw the perfect opening for his brilliant protégé. He recommended Euler with the highest praise, alongside his own two sons, Nicholas and Daniel Bernoulli, who were already established as formidable mathematicians in their own right. In 1727, at the age of 20, Euler accepted the invitation and embarked on the long journey to St. Petersburg, leaving the familiar world of Basel for a city that was itself a grand and unfinished experiment. His arrival at the nascent academy reveals much about the fluid disciplinary expectations of the 18th century Enlightenment. The position that awaited him was in the medical faculty as a professor of physiology. This appointment, which seems peculiar to the modern specialized mind, was a consequence of the available vacancies and the polymathic ideal of the era. A first-rate intellect was presumed capable of contributing across a spectrum of sciences. Euler, ever practical and possessing a capacious mind, had prepared for this role by immersing himself in the study of medicine and physiology, even attending lectures on the anatomy of the ear and the physics of sound. This brief sojourn into physiology was far from a waste. His later work in acoustics and the physics of wave propagation would bear the marks of these early cross-disciplinary investigations. However, the sheer force of his mathematical genius could be channeled into other fields for only so long. The tragic, early deaths of Nicholas Bernoulli and the Empress Catherine created a period of turmoil and reshuffling at the Academy. Daniel Bernoulli moved from the mathematics chair to physics, and the vacancy in mathematics was immediately and naturally filled by the young man who had been dazzling his colleagues with his computational power and analytical insight from the moment he arrived. By 1731, Leonhard Euler was the Academy's chief professor of mathematics. He had found his home in the vibrant, well-funded and intellectually ambitious environment of the St. Petersburg Academy, with few teaching duties and a mandate to produce original research. Euler was perfectly positioned. The mathematical world, rich with possibility and aching for order, lay before him. He was ready to begin the work of giving it a soul. With his appointment as the Academy's chief professor, Euler inherited a discipline of immense power and yet profound disarray. The infinitesimal calculus, bequeathed by Newton and Leibniz, was a tool of almost miraculous efficacy. It could calculate the slope of a curve at any point, find the area beneath it, and describe the dynamics of a moving planet. For all its utility, however, it was a wild garden of brilliant insights, lacking a common language, a coherent structure, or a unifying principle. Different mathematicians used their own idiosyncratic notations, making communication a frustrating exercise in translation. Proofs often relied on vague geometric intuitions or appeals to physical motion, their foundations philosophically precarious. The great intellectual machine of calculus was operational, yet its engineering schematics were missing. Euler surveyed this landscape of powerful disconnected techniques and perceived his true calling to provide the architecture for a new world of mathematics, a world of analysis. His first and perhaps most enduring contribution was an act of profound linguistic clarification. He understood that for mathematics to advance, it required a universal vocabulary,
a set of symbols so clear and powerful they would become extensions of thought itself. He began by introducing the simple, elegant notation phi of x, written f a parenthesis x, to represent a function of a variable x. This conceptual leap was monumental. It abstracted the very idea of a mathematical relationship, freeing it from the specific geometry of a curve or the algebra of a particular polynomial. A function became an object in its own right, a machine that takes an input, x, and produces an output, f of x, according to a defined rule. This single innovation allowed mathematicians to speak of entire families of relationships, to analyze their general properties, and to build theories about functions themselves. To this he added the other cornerstones of the modern mathematical alphabet. He designated the letter E as the base of the natural logarithms, a curious and transcendental number approximately equal to 2.718, which appears organically in any system involving continuous growth or decay. He championed the use of the Greek letter P for the ratio of a circle's circumference to its diameter, solidifying its status as a fundamental constant. He took the square root of -1, an entity whose existence was a source of metaphysical anxiety for many, and gave it the simple, confident name I, the imaginary unit. With this he laid the groundwork for the entire field of complex analysis. For the process of summation, he introduced the capital Greek letter sigma, a compact and unambiguous way to express the addition of a long or even infinite sequence of terms. These symbols were instruments of clarity. They streamlined calculation, facilitated communication across Europe, and most importantly enabled a higher level of abstraction. Mathematics could now be conducted in a symbolic language of its own, its arguments proceeding with an algebraic crispness that geometric reasoning could seldom match. With this new lexicon established, Euler embarked upon his magnum opus of unification, the two-volume masterpiece published in 1748, the Introductio in Analysin Infinitorum, or Introduction to the Analysis of the Infinite. This was the work that formally gave birth to the field of analysis as we understand it today. It was, in essence, the founding constitution for modern mathematics. The central revolutionary thesis of the Introductio was the elevation of the function concept to the absolute heart of the discipline. For Euler, a function was any analytic expression composed of variables and constants. This definition swept away the old hierarchies. Algebra, trigonometry, and analytic geometry were subsumed into a single, magnificent intellectual framework. The implications were staggering. Trigonometry, for instance, was transformed. Its focus moved from the ratios of sides in a right-angled triangle to the study of the sine, cosine, and tangent as periodic functions. These were waves repeating patterns that could be described by Euler's functional notation, sine of x and cosine of x, and whose properties could be explored using the full power of algebra and calculus. Logarithms and exponential expressions were likewise treated as functions, their inverse relationship explored with unprecedented depth. The entire subject we now call pre-calculus was, in large part, codified and organized for the first time within the pages of the Introductio. Euler had created the textbook that would educate generations of mathematicians and scientists, establishing a common curriculum and a shared understanding of the fundamental objects of their study. He had taken the scattered brilliant fragments of 17th-century mathematics and forged them into a coherent, powerful, and beautiful whole. The grand synthesis achieved in the Introductio finds its most sublime and breathtaking expression in a single, compact equation, often called the most beautiful in all of mathematics. It is Euler's identity, e to the power of I pi plus 1 equals 0. This is far more than an intellectual curiosity. It is the ultimate statement of the deep hidden unity that his work on analysis revealed. Within this one line of reasoning, the 5 most fundamental constants of mathematics are brought into a relationship of shocking simplicity. There is E, the base of natural growth, the symbol of analysis and calculus. There is I, the imaginary unit, the heart of algebra's extension into the complex plane. There is pi, the constant of the circle, the soul of geometry. And there are 1 and 0, the foundational elements of arithmetic, the identities of multiplication and addition. This equation is a line of poetry written in the language of the cosmos. It declares that the number governing continuous growth, when raised to the power of the geometric constant multiplied by the imaginary unit, results in -1. It connects the world of the transcendental with the world of the algebraic and the geometric. It is the perfect crystalline culmination of Euler's quest to demonstrate that the disparate branches of mathematics were all whispers of a single underlying truth. He had provided the language, he had defined the central subject, and in this identity he revealed the profound interconnected harmony of the entire mathematical universe. The groundwork was now complete. Upon this solid foundation of a unified analysis, he could begin to erect even grander structures, applying this powerful new machinery to confront the most formidable challenges of the infinite dot. This equation is a line of poetry written in the language of the cosmos. It declares that the number governing continuous growth, when raised to the power of the geometric constant multiplied by the imaginary unit, results in -1. It connects the world of the transcendental with the world of the algebraic and the geometric. It is the perfect crystalline culmination of Euler's quest to demonstrate that the disparate branches of mathematics were all whispers of a single underlying truth. He had provided the language, he had defined the central subject, and in this identity he revealed the profound interconnected harmony of the entire mathematical universe. The groundwork was now complete. Upon this solid foundation of a unified analysis, he could begin to erect even grander structures, applying this powerful new machinery to confront the most formidable challenges of the infinite. With the architecture of analysis firmly established, Euler turned his attention to problems that had long stood as monuments to the limits of mathematical inquiry. Among the most famous of these was a question concerning the summation of an infinite series, a puzzle that had vexed the brilliant Bernoulli dynasty for decades. The problem, which had acquired the name of the city of Basel, was deceptively simple to state. It asked for the precise value of the sum of the reciprocals of the perfect squares 1 plus 1/4 plus 1/9 plus 1/16, and so on, continuing forever. The series clearly converged to a finite value. Its terms diminished rapidly, and numerical approximations suggested a sum around 1.645. The challenge lay in finding the exact closed-form expression for this limit. For 40 years, the problem resisted all attempts at a formal solution, becoming a benchmark of mathematical prowess. Euler's resolution to the Basel problem, presented in 1734, remains one of the most breathtaking feats of mathematical intuition in history. His method possessed an audacity that flew in the face of conventional step-by-step deduction, relying instead on a profound analogy. He began with a familiar function from his analytical framework, the sine of x. He expressed this function, as was common, through its infinite power series expansion, which is x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial, and so forth. He then considered the roots of the equation sine of x equals 0, the values of x for which the function vanishes. These roots are well known. 0 pi, negative pi, 2 pi, negative 2 pi, and on to infinity in both directions. Here Euler made his spectacular leap. He recalled that a finite polynomial can be written as a product of factors corresponding to its roots. For instance, a quadratic with roots alpha and beta can be written as a constant times the quantity x minus alpha times the quantity x minus beta. Euler reasoned that this principle should extend to the infinite polynomial represented by the sine function series. He constructed an infinite product using the roots of sine of x, expressing it in the form 1 minus x squared over pi squared times the quantity 1 minus x squared over 4 pi squared times the quantity 1 minus x squared over 9 pi squared, and continuing for all the non-zero roots. He then set the original power series for sine of x equal to this new infinite product of its factors. By dividing both sides by x, he had two different infinite expressions for the same function, sine of x divided by x. One was a power series, beginning with 1 minus x squared over 6 plus higher order terms. The other was his infinite product. By the logic of polynomial identities, the coefficients of corresponding powers of x on both sides must be equal. Euler focused on the coefficient of the x squared term. In the power series, this coefficient was negative 1/6. In the infinite product, expanding the terms revealed that the x squared coefficient was the negative sum of 1 over pi squared plus 1 over 4 pi squared plus 1 over 9 pi squared, and so on. Equating these two coefficients yielded a stunning equation. Negative 1/6 equals the negative of the sum of 1 over n squared pi squared. A simple algebraic rearrangement revealed the long-sought answer. The sum of the reciprocals of the squares was exactly pi squared divided by 6. The mystery was solved. This result was electrifying. It forged an unforeseen link between the integers and the transcendental number p, suggesting a deep hidden structure connecting arithmetic and geometry. While the full rigorous justification for treating an infinite series like a finite polynomial would await the work of Weierstrass, a century later, Euler's confidence in the ultimate consistency of his analytical world was completely vindicated. His answer was correct, and it opened the door to a whole new understanding of infinite sums and their relationship to fundamental constants. This command over the infinite extended naturally into the domain of dynamics and change. The calculus of Newton and Leibniz had provided the tools to describe instantaneous rates of change, yet solving the equations that arose from these descriptions remained a bespoke, often frustrating art. These differential equations, which relate a function to its derivatives, were the mathematical language of physics, essential for describing everything from planetary orbits to the vibration of a string. Before Euler, however, the field was a patchwork of clever tricks applicable only to specific forms of equations. A general systematic approach for finding solutions was desperately needed. Euler answered this need by forging the first comprehensive theory for solving a broad and vital class of these equations. He focused on linear ordinary differential equations with constant coefficients, the very type that appears constantly in models of physical systems. His central insight was to assume a solution of a particular exponential form, or equals e to the power of r times x, where r is some constant. Substituting this guess into the differential equation had a magical effect. Because the derivative of an exponential is another exponential, the calculus problem was transformed into a purely algebraic one. The differential equation became a simple polynomial equation in the variable r, which we now call the characteristic equation. The power of this method lay in its completeness. Euler systematically explored all possibilities. If the roots of the characteristic equation were real and distinct, the general solution was a linear combination of the corresponding exponential functions. If a root was repeated, he demonstrated how to construct additional, linearly independent solutions by multiplying the exponential by powers of x. Most beautifully, when the roots were complex numbers, his own identity, e to the power of I times theta equals cosine of theta plus I times sine of theta, allowed him to transform the complex exponential solutions into real-world oscillating solutions involving sines and cosines. This provided the mathematical foundation for describing all forms of simple harmonic motion and wave phenomena. Furthermore, Euler introduced another powerful general-purpose tool, the integrating factor. He recognized that many first-order differential equations that were otherwise intractable could be made solvable if one could find a special function to multiply them by. This integrating factors was engineered to turn one side of the equation into the perfect derivative of a product of functions, a form that could then be resolved by a straightforward integration. Finding this factor was itself a new problem, but he provided methods for doing so in many important cases. This technique converted a puzzle into a procedure. With these contributions, Euler converted the solution of differential equations from an art form into a science. He gave mathematicians and physicists a reliable algorithmic toolkit for tackling a vast array of problems that were previously out of reach. His methods for solving constant coefficient linear equations and his concept of the integrating factor remain the first and most fundamental techniques taught in any introductory course on the subject today. They form the bedrock upon which much of modern physics and engineering is built. The intellectual machinery he constructed for analysis, born from unifying the concept of a function and taming the infinite, was now fully deployed. His methods could dissect the continuous processes of nature with the same certainty and clarity he brought to the discrete sums of numbers. His analytical vision was so powerful and all-encompassing that it would soon illuminate areas of mathematics that seemed to exist in entirely different universes from calculus, revealing their own deep and unexpected connections to the world of number and function. The analytical vision that had so masterfully unified the calculus and given it the power to dissect the continuous processes of nature was now poised to illuminate domains of mathematics that seemed to exist in entirely different universes. This same penetrating intellect would turn from the world of flowing functions and infinitesimal changes toward the most discrete of realms, the integers themselves. Concurrently, it would find in a simple recreational puzzle the seeds of a new geometry, one concerned with pure connection. In these explorations, Euler would erect two more monumental pillars of modern mathematics, analytic number theory and graph theory. Prior to Euler's sustained attention, the study of whole numbers existed largely as a cabinet of elegant curiosities, a collection of profound conjectures and isolated results, bequeathed primarily by the brilliant French jurist Pierre de Fermat. These were beautiful, tantalizing statements about prime numbers and their properties, often scribbled in the margins of books with the infamous claim of a proof too large to fit. The field awaited a systematic architect, someone with the patience to supply the missing proofs, and the vision to see a grander structure connecting these disparate observations. Euler became that architect. He was one of the few mathematicians of his era who took Fermat's assertions seriously, and he dedicated decades to the patient, rigorous work of proving them. He furnished the first published proof of what is known as Fermat's little theorem, a cornerstone result, stating that for any prime number p and any integer a, the quantity a to the power of p minus a is divisible by p. Having affirmed this, Euler's mind characteristically sought a broader, more powerful principle. His investigation led him to formulate one of his most celebrated creations, the totient function. This function, denoted phi of n, counts the positive integers up to a given integer n that are relatively prime to n. With this tool, he constructed Euler's totient theorem, a powerful generalization of Fermat's work. It applies to composite numbers as well as primes, and became a far more versatile instrument in the study of modular arithmetic. For 2 centuries, this theorem remained a beautiful piece of pure mathematics, an exemplar of the intricate, abstract beauty hidden within the integers. Today, it forms the indispensable mathematical engine behind the RSA algorithm, the public key crypto system that secures a vast portion of modern digital communication and commerce. A principle uncovered through pure intellectual curiosity now serves as the cryptographic lock for the global economy. His most revolutionary contribution to number theory, however, was the creation of a stunning and entirely unexpected bridge between 2 worlds. He connected the discrete granular universe of prime numbers with the smooth flowing world of analysis. He achieved this through his investigation of the harmonic series, the sum of reciprocals of all positive integers. While it was known that this sum diverges to infinity, Euler asked a more subtle question: what is the sum of the reciprocals of the squares of the integers? This is the famous Basel problem, which had stumped the leading mathematicians of the day. Euler's solution, that the sum is precisely pi squared divided by 6, was a triumph. His method involved representing the sine function as an infinite product of its roots, a leap of analytical intuition that was both audacious and, as it turned out, correct. This success led him to consider a more general function, what we now call the Riemann zeta function, defined as the sum of the reciprocals of the integers raised to some power. For this function, he derived one of the most beautiful formulas in all of mathematics, the Euler product formula. It states that the zeta function of s is equal to an infinite product taken over all prime numbers piece of the term 1 divided by 1 minus piece to the power of negative s. This equation forged an explicit, profound link between the zeta function, an object of analysis, and the prime numbers, the fundamental atoms of arithmetic. It meant that questions about the distribution of primes could be reformulated as questions about the behavior of a complex function. This single formula inaugurated the entire field of analytic number theory, a discipline that uses the powerful tools of calculus and complex analysis to probe the deepest mysteries of the integers. As he was laying these foundations for the modern study of number, Euler's attention was captured by a seemingly trivial local curiosity. The city of Königsberg in Prussia was set on the Pregel River and included 2 large islands connected to each other and the mainland by 7 bridges. A popular puzzle of the day asked whether it was possible to take a walk through the city that would cross each of the 7 bridges exactly once. The citizens of Königsberg had, through trial and error, come to believe it was impossible, but a mathematical proof was absent. The problem had no home in the existing mathematics of the day. It was a question of arrangement, of pure structure, independent of distance, angle, or any of the usual concerns of geometry. Euler's genius was to recognize that the specific layout, the lengths of the bridges, or the sizes of the landmasses were entirely irrelevant. He abstracted the problem into its essential form. He represented each of the 4 landmasses as a point or a vertex, and each of the 7 bridges as a line or an edge, connecting these vertices. The result was a simple diagram, a network stripped of all its geographic and metric properties. With this, he transformed a recreational puzzle into a question about the properties of an abstract graph. He then analyzed the structure of this graph, focusing on the degree of each vertex, which is the number of edges connected to it. He reasoned that in any walk traversing every edge exactly once, every intermediate vertex must have an even number of edges connected to it, one for entering and one for leaving. A path could start or end at a vertex with an odd degree, but there could be at most two such vertices for a complete traversal. In the Königsberg graph, all four vertices had an odd degree. Therefore, he proved with irrefutable logic, such a walk was impossible. His 1736 paper, Solutio Problematis ad geometriam cetus pertinetis, or the solution of a problem relating to the geometry of position, did far more than solve a brain teaser. It gave birth to the field of graph theory and laid one of the first foundational stones of topology. By demonstrating that a mathematical problem could be solved by studying properties of connection and arrangement that are preserved under continuous deformation, he opened the door to a new kind of geometry. Today, the language of graphs and networks he pioneered is indispensable. It provides the mathematical framework for everything from the internet and social networks to airline logistics, molecular biology, and neural computation. The simple walk through Königsberg became a journey into the very heart of modern network science. These twin achievements, in number theory and graph theory, showcase Euler's unique capacity to perceive profound, underlying structures and to forge entirely new mathematical tools to understand them, preparing the way for his equally groundbreaking applications of mathematics to the physical world. The same analytical power that uncovered the hidden architecture of numbers and networks was soon directed toward the tangible universe of matter and motion. The Enlightenment's scientific enterprise, having absorbed the revolutionary principles of Newton's Principia, faced a new, formidable challenge. Newton had bequeathed a set of universal laws, elegant in their abstraction, describing how forces produce acceleration. The monumental task that remained was to translate this grand abstract framework into a predictive analytical science, capable of describing the intricate behaviors of real-world objects. The wobble of a spinning planet, the turbulent rush of a river, the precise failure point of a load-bearing column. It was Leonhard Euler who accepted this challenge, forging the mathematical machinery that would transform Newtonian physics into the bedrock of modern engineering. He constructed the bridge between abstract law and concrete prediction, building the discipline we now recognize as mathematical physics. His first conquest was in the realm of mechanics, specifically the complex and confounding problem of rotating rigid bodies. While Newton's laws worked beautifully for idealized point masses or spherically symmetric planets, they offered little immediate guidance for the motion of an irregularly shaped object spinning in three-dimensional space. The precession of the equinoxes, the wobble of a child's spinning top, the tumbling of a thrown stone, these phenomena defied simple analysis. The difficulty lay in the object's extension in space. Different parts of the body move at different velocities and in different directions simultaneously. A new conceptual apparatus was required. Euler provided it by introducing the foundational ideas of principal axes of inertia and moments of inertia. He conceived of any rigid body as having three mutually perpendicular axes of rotation passing through its center of mass. When the body spins around one of these special principal axes, its angular momentum vector aligns perfectly with its angular velocity vector, resulting in a stable, balanced rotation. From this geometric insight, he derived the famous Euler equations of motion. This set of three coupled first-order differential equations describes the evolution of a body's angular velocity over time. The equations relate the applied external torques to the rate of change of the body's angular momentum, expressed in a coordinate system that rotates along with the body itself. This choice of a rotating reference frame was a stroke of genius, simplifying the otherwise intractable mathematics. For the first time, humanity possessed a complete and quantitative theory for the dynamics of any rotating object. The implications were immediate and profound. These equations provided the first rigorous explanation for the precession of the Earth's axis, a puzzle that had perplexed astronomers for millennia. They form the theoretical basis for the gyroscope, an instrument essential for navigation in everything from aircraft to spacecraft. Every time an aerospace engineer stabilizes a satellite or a physicist analyzes the spin of a molecule, they are working within the conceptual world Euler constructed. His attention then turned from solid bodies to the even more daunting challenge of fluids. Describing the flow of water in a channel or air over a wing presented a problem of immense complexity. One could, in principle, track every single particle of the fluid using Newton's laws, an approach we now call the Lagrangian perspective. The sheer impossibility of such a calculation for a continuous medium was self-evident. Euler pioneered a revolutionary alternative, the Eulerian perspective, which remains the standard approach in the field. He proposed observing the fluid from fixed points in space, describing how the fluid's properties, its velocity, pressure, and density change at each point over time. This conceptual shift from tracking particles to describing a field was a pivotal moment in the history of physics. From this viewpoint, he formulated the Euler equations of fluid dynamics. These are a set of partial differential equations expressing the conservation of mass, momentum, and energy for a moving fluid. In their most common form, they state that the acceleration of a fluid element is determined by the forces acting upon it, specifically the gradient of the pressure within the fluid and any external body forces like gravity. A crucial characteristic of these equations is that they describe an ideal or inviscid fluid, one completely devoid of internal friction or viscosity. While this represents an idealization, the Euler equations provide an exceptionally accurate description for a vast range of important flows, particularly in aerodynamics and gas dynamics, where viscous effects are confined to thin boundary layers. They are the starting point for the entire modern edifice of fluid mechanics. The more comprehensive Navier-Stokes equations, which do account for viscosity, are a direct extension of Euler's original framework. From designing the airfoil of a supersonic jet to modeling the flow of blood through an artery or the circulation of a planetary atmosphere, the intellectual journey begins with the elegant and powerful field description of fluid motion that Euler created. This drive to apply mathematical rigor to physical problems extended to the practical arts of engineering and optics. He addressed the critical engineering problem of structural stability, asking a question of immense practical importance: what is the maximum load a slender column can support before it suddenly and catastrophically buckles? Through a masterful application of his calculus of variations, Euler derived the formula for the critical buckling load. He demonstrated that failure occurs through a mode of elastic instability, a phenomenon where the column, under a specific compressive force, deflects laterally and collapses. The Euler buckling formula reveals that this critical load depends on the column's length, its material stiffness, the modulus of elasticity, and the geometry of its cross-section, specifically its area moment of inertia. This was a landmark achievement, marking one of the first times a purely theoretical, mathematical analysis yielded a precise quantitative prediction for mechanical failure. It remains a cornerstone of structural and civil engineering, informing the design of everything from building supports to aircraft struts and bridge trusses. In the field of optics, he tackled the vexing problem of chromatic aberration, the color fringing seen in images produced by simple lenses. This effect arises because the refractive index of glass varies with the wavelength of light, causing different colors to be focused at slightly different points. The result was that 18th century telescopes and microscopes produced images with blurry colored halos, limiting their power and precision. Euler theorized that this defect could be corrected, believing the human eye itself to be an achromatic system. He performed a deep mathematical analysis of the refractive properties of different media and proposed a solution, the achromatic lens. This was a compound lens built from two separate elements made of different types of glass, such as crown and flint glass, which have different dispersive properties. By carefully calculating the curvatures of these two lenses, he showed how they could be combined into a single system that would bring light of different colors to a common focus. Though his initial attempts to construct such a lens were hampered by the quality of available glass, his theoretical work laid the indispensable foundation. The English optician John Dolland, following Euler's principles, successfully produced the first practical achromatic lenses, revolutionizing the construction of telescopes and microscopes and opening new windows onto the macroscopic and microscopic worlds. In each of these domains, the mechanics of rotation, the flow of fluids, the stability of structures, and the behavior of light, Euler's work followed a consistent and powerful pattern. He identified a fundamental physical problem, reformulated it in the precise language of calculus, and solved the resulting equations to produce insights and predictive tools of enduring power, thereby building the very foundations of applied physical science. The principles of mechanics and optics he so masterfully articulated found their final, and perhaps most astonishing, application within the chambers of his own mind. In 1766, at the express invitation of Catherine the Great, a monarch who prized intellectual prestige as a cornerstone of imperial power, Euler made his final journey. He returned to St. Petersburg, the city where his career had first blossomed, to preside over its Academy of Sciences once more. This return, however, marked the beginning of a new and extraordinary chapter, one conducted almost entirely in the dark. A cataract in his remaining good eye, which had been his window to the world for 3 decades, began to fail. An operation proved unsuccessful, and within a few years, Leonhard Euler, the man who saw the hidden architecture of the universe with unparalleled clarity, was rendered almost completely blind. For any other intellect, such a fate would have signaled a quiet retirement, a descent into silence. For Euler, it acted as a peculiar and powerful catalyst. Freed from the potential distractions of the visual world, his mind turned inward, accessing a universe of forms and relationships with an intensity that perhaps even he had seldom before experienced. The external blackboard was replaced by the infinite slate of his memory, a faculty so prodigious it remains a source of wonder. He could recite Virgil's Aeneid from beginning to end, and more to the point, could perform staggering mental calculations, holding complex algebraic manipulations in his head through dozens of steps. His study became a collaborative workshop. He dictated his thoughts, his equations, his proofs to his sons, particularly Johann Albrecht, and to a young Swiss assistant, Nicholas Voss, who would become his devoted amanuensis. They were the hands that gave physical form to the torrent of ideas flowing from a mind that now worked without interruption. The result was an intellectual eruption of historic proportions. In the 17 years from his return to St. Petersburg until his death, laboring in near-total darkness, Euler produced nearly half of his lifetime's colossal output. Hundreds of papers poured forth, touching upon every corner of mathematics and physics. He dictated a complete 2-volume treatise on integral calculus, the Institutiones Calculi Integralis, which became the definitive text on the subject for a century. He composed works on optics, mechanics, and lunar theory, resolving with his mental vision problems of celestial motion that had baffled his contemporaries. He would often amuse himself by constructing magic squares or solving numerical puzzles while his grandchildren played at his feet, his mind simultaneously engaged with the most profound questions of science. This period demonstrates a cognitive phenomenon, the power of a mind so completely saturated with the language of mathematics that it could perceive, manipulate and create within that symbolic realm as effortlessly as we perceive the physical world around us. His blindness removed a medium, it enhanced the immediacy of his thought. Reflecting on this immense body of work, one arrives at the understanding articulated by Pierre-Simon Laplace a generation later. Read Euler, he is the master of us all. This was a statement of profound accuracy. Euler's ultimate legacy is the very language of analysis itself. He bequeathed to his successors, to Lagrange, to Laplace, to Gauss, a complete operational calculus, a system of notation, and a set of foundational concepts that form the bedrock of their own monumental achievements. The symbols we take for granted, the very grammar of modern mathematics, are largely his creation. The letter E for the base of natural logarithms, the Greek letter pi for the ratio of a circle's circumference to its diameter, the letter I for the imaginary unit, the square root of -1, the sigma notation for summation, and the functional notation for x. He created the atmosphere that the next century of mathematicians would breathe. They worked within an Eulerian framework, extending his methods, applying his functions, and building upon his theorems. He provided the tools, and in doing so, he shaped the questions that could be asked and answered for the next 100 years. His work embodies the highest ideals of the Enlightenment, the grand intellectual movement that defined his era. Euler's universe was one of inherent order, a cosmos governed by rational laws that were accessible to the human intellect through the power of mathematics. He pursued a unified vision of knowledge, seeing a seamless continuity from the abstract elegance of number theory to the concrete challenges of shipbuilding and hydraulics. For him, the partial differential equation describing the vibration of a string shared a deep intrinsic beauty with the infinite series representing pi. This belief in a rational, comprehensible, and unified reality drove his relentless quest to mathematize every aspect of the physical world. He was the ultimate system builder, constructing vast, coherent edifices of thought where others had left scattered insights. Through his work, the Enlightenment's faith in reason found its most powerful and enduring expression, demonstrating that the world was a book written in the language of calculus, a book he was uniquely gifted to read. The echoes of that reading resonate throughout our modern technological civilization. The analytical methods he pioneered are embedded in the very fabric of our world. The equations of fluid dynamics govern the design of aircraft and the prediction of weather. His principles of mechanics and elasticity are essential for the construction of bridges and skyscrapers. The Fourier analysis that underpins all of modern signal processing, from digital audio to medical imaging, is a direct descendant of his work on trigonometric series. His graph theory laid the groundwork for network science, which maps everything from the internet to social interactions. Leonhard Euler's mind, working in a quiet study in Berlin or dictating in the darkness of St. Petersburg, constructed a significant portion of the intellectual infrastructure upon which the 21st century is built. His life concluded as it was lived in the midst of intellectual discovery. On September 18, 1783, after an afternoon spent calculating the laws of ascent for hot air balloons, a brand new technology that had captured his imagination, and enjoying a quiet dinner with his family, he suffered a sudden cerebral hemorrhage. His final recorded words, as he sketched a calculation on his slate, were, "I die." It was a swift, peaceful end to a life of unparalleled intellectual vigor. He left behind a legacy of nearly 900 books and papers, a body of work so vast that the St. Petersburg Academy continued to publish his manuscripts for almost 50 years after his death. This astonishing fecundity, this comprehensive mastery, this serene and relentless dedication to the pursuit of knowledge secures his place in the pantheon of science. He was a universe of thought contained within a single mind, a figure who represents the sublime and enduring power of reason to illuminate the world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.